I appreciate there's like only a couple of us here. And then I ask myself, why isn't more of the security community doing something with this? The people in this room, are you doing anything with quantum computing, key distribution? Anyone? Yeah, it's already tangible. So let's talk about what this is and why we're concerned. The reason I think that every security officer should know about this is because it actually represents a real challenge for us as a community. So my job at KPN, my mission with the rest of my team, is to keep KPN reliable, secure, and trusted by customers, partners, and society. We're part of the vital infrastructure of the Netherlands. We're a company that's been around as the incumbent since 1895. So it means that that mission isn't temporary. We've been around for the last 100 years. We need to be around for the next 100. And in order to do that, we need secrecy that is going to go forward in the future, not only for our own data, but also for that of our customers. So let's talk about what I'm going to talk about. I would really like to go through with you in the next 20 minutes, 30 minutes that we have, what we have as the problem and what we're going to do about it. So I'd like you to understand, why we have this starting base of quantum and what the actual issues are around it. We're going to also talk about what you can actually do about it. So explain the plan and look at developments by other people to see how far we are with actually getting there. So let's talk about the threat for a moment. I don't think I need to tell any of you that the intelligence agencies that are around the planet today have complete informational awareness. At any time, they know who you're talking to, how you're moving, and they know what you're doing. That enormous capability is still something that the intelligence agencies have a problem with, that it's not enough. And why isn't enough? Because they're afraid of the going dark problem. The going dark problem is that there are pockets that that total information awareness doesn't extend to. And those pockets are limited for the intelligence agencies because of the use of cryptography for them. And because of that, what we saw is that, the Snowden revelations actually kind of told us how far this capability extended to. But you don't see everyone still being adamant, worried, actually adopting secure communications protocols, running out to go buy Silent Circle and the Black Phone, which I really would have liked them to do, but they didn't. And the question is why? Is it because they don't know, or they just don't really care? And finally, what we see is that, regardless of this en masse shared public opinion, we see a renewal in all countries of the original crypto wars from the 1990s. And this is a problem because really we're not as equipped today, in fact, to deal with it. When the threats get very, very close, we seem to succumb to losing our principles around privacy and security. And as Phil likes to say, and I'm going to quote you because you're there, and I remember you said this to me, national security is the root password for any government. So if you say national security, you can pretty much get away with anything, infringing on any other right. So if you take a look at the NSA programs that talk about quantum research, they talk about a black budget. So it's a budget where they don't have to actually explain what they're spending on when it comes to doing this research. So the two projects that they talked about were penetrating hard targets and owning the net. The penetrating hard targets one was to actually look to break quantum to develop a quantum computer and bake quantum encryption, and they were going to do that with a quantum computer that was going to have 5 qubits. 5 qubits is not that impressive. In fact, that's the size of the currently released publicly usable quantum computer by IBM. The other project was owning the net, which was actually looking at doing offensive operations to break cryptography. The clue here is that all intelligence agencies have a dual-use kind of purpose in life, a raison d'etre. And what that is they have to have signal intelligence capabilities, so they have to break everybody else's crypto and be able to get that traffic. And at the same time, they have to have information assurance, so they have to keep their own stuff secret. That's hard to do. So I want to develop a sort of, and this is where the original crypto wars came from. I want to keep all my secrets secret. I just don't want you to have any. And that kind of dichotomy becomes difficult to actually carry out well in practice. So let's take a look at what we're talking about when we talk quantum. I mean, I think the clue is that a lot of people are thrown off because they think it's complex. Actually, it is kind of complex, but it just takes some time for us to get to understand and grips with as a security community. So if we compare it in terms of classical physics, we know about it really, because it's all the stuff that kind of happened in terms of evolution before 1900. It really talks about big stuff in the macroscopic world. It's highly deterministic, which means that if you have an action, you have a resulting and opposing reaction. So we can kind of explain what's happening there, and we already know the outcome. It's also highly intuitive. And when we compare that with things that are quantum physics or quantum mechanics, it's predominantly after 1900. The real fathers of quantum mechanics are people like Niels Bohr. So it's like, and you had the conference in 1920 in Belgium, which really kind of was the birthplace with a lot of modern physicists of the quantum mechanics era. It actually describes the microscopic world. It's also highly probabilistic, which means that we don't always know exactly what's going to happen, but we can kind of calculate the probability of the actual resulting reaction of the action that's initially happened. There's also a very central role of the observer, and it's highly non-intuitive. So it really requires us to be able to observe everything that's going on and try to figure out what's happening, which is not always natural like it would be in classical physics. And what we also see is that when we're looking at quantum physics and their reactions, it always happens in hyper-cooled environment. Because we're looking at the incredibly small, in order to be able to have this central role of the observer, we need to slow stuff down. That means we're talking about 100 degrees under Kelvin when you're actually looking for these quantum reactions to happen. I suppose the question is, when will the post-quantum era arrive? And that's an era when there is the possession of quantum computers. So what are the properties of a quantum computer? Regular classical computers have bits. Quantum computers have qubits. So a regular computer has a 0 or a 1. A quantum computer has a 0 and a 1 at the same time. They're superpositioned, and this superpositioning allows it to have already scale over a classical computer. What's also really cool is that this principle of entanglement. Entanglement is the thing that would give a quantum computer scale, but it's also the thing that's used in order to create trusted node networks when we have quantum key distribution. So entanglement means that you have two particles. I'm just going to see if the pointer works here. So we know about Alice talking to Bob, but imagine that Alice is so entangled with Bob that trying to measure something that Alice has done will actually also result in a measurement on Bob's side. These are a maximally entangled pair of photons, and these types of measurements mean that if someone is trying to screw around with either Alice or Bob, we know. Yeah, and I'm trying to make this as simple as possible, but it's this idea that despite large distances, these things are maximally entangled. This is a difficult concept in physics, and actually, Einstein called it spooky action at a distance. And for ages, physicists have actually been trying to prove that this phenomenon occurs and that it can be observed. So recently, and it was published in Nature last year in October, you have Professor Ronald Hansen at the Technical University of Delft, who actually conducted a loophole-free Bell test, which means that he had two maximally entangled photons at a distance of 4 kilometers, and when infecting the one, he could prove by measurement that the other was also affected. Think about this for a moment, because these reactions are known to be happening faster than the speed of light. However, this cannot be considered communication. So faster than the speed of light, because we know when we're measuring it, if you measure them at the same time, that you have here a photon, which if you try to alter it or maneuver it or turn it, and I just told you before about the qubit, which exists as a 0 or a 1 at the same time, let's assume that for them to be maximally entangled, that one will be the 0 and the other will be the 1. In reality, it doesn't always work that way, because if you actually look at the physical requirements for entanglement, you'll see that both of those resulting things always have to equal 0. But it means that they are so incredibly entwined that you can prove that they are always communicating. So I've turned something there, and faster than the speed of light, this has also changed. I think that's a really funky concept just by itself, regardless of what we can do with it. But the ability to do this is to take it out, build quantum trusted nodes across the internet that are always entangled, that are always in this unperturbed state. Quantum has particular properties, the first of which is fragility. These things are very, very, very finicky. If you try to observe them under non-optimal conditions, if there's noise, etc., they break down. These states collapse. So coherence is a very important thing when you're trying to establish qubits. The other thing is what we just talked about, which is, the actual observation destroys the quality of the communication between Alice and Bob, and that's because there's a no cloning principle. You cannot copy this communication without being observed. So, what's the quantum computer about? Well, the quantum computer is about using all the properties that we just mentioned to build a machine that will be capable of doing really amazing things. The first and foremost thing that it's probably going to be used for is to actually break the current cryptography that we know now. But there's more than one type of quantum computer, and I don't think that everybody's aware of that. The first type of quantum computer that we have, where it's actually not that difficult to build the necessary qubits, is a quantum annealer. This is, if you've ever heard of the company D-Wave, this is the type of machine that D-Wave has. D-Wave has a quantum annealer. And it's a very simple to build machine. There's not that much difficulty in building it, but it allows you to really, have a viable set of qubits to perform certain operations. The second type of quantum computer we have is an analog quantum computer. And this is a little bit more difficult, and it's really kind of probably the first thing that's going to happen in the soonest amount of time, which does have viability to do more operations than the annealer will. But we're seeing that really the holy grail, the thing that everybody is building, including the University of Delft, where we're from, is the universal quantum computer. And this is the real challenge in quantum computing. This is the stuff that IBM are working on. This is the thing that Google is also working on in their own labs. A lot of people are working on this because this is the thing that's going to be able to do all of the functions that were originally foreseen that we cannot yet do with classical computing. And why can't we do this with classical computing? Well, there's this principle called Amdahls Law, which means that the more processors you add to a particular computing problem won't actually result in the necessary output. It's not linear. So you can keep adding stuff, more processing power, but it won't actually result in more capability to do the computational things that you're looking for. So Amdahls Law is the thing that's actually making us kind of drive forward to have this quantum computing machine. The two algorithms that we originally thought of that would require the use of a quantum computer. The first one of them is called Shor's algorithm, and Shor's algorithm is doing integer factorization, which would be the thing that we would need for a public key crypto system. In order to be able to figure out what those keys were, we would need Shor to do that. And Grover's is actually delivering a sort of computational speed up, because it allows us to search quickly through databases for finding that key. So the needle in the haystack problem. There's other really cool stuff that a quantum computer can also do. They're talking about simulating science experiments, being able to solve billion-dollar problems with fixing nitrogen for all types of industrial processes. So there's a lot of really nice science modulation stuff that they're doing, that they're thinking that they could do, actually, with a quantum computer. And what we should realize, and I don't think in the security community this is well known, is that everybody's doing this. This is an arms race in terms of the fact that everybody wants to get there first. And when they get there first, we won't hear about it. This is equivalent to something like the Manhattan Project, where scientists were moved to a secret location with their entire family set there to work on one problem, because being there first is vitally important for national security, root password. So really, this is a huge challenge, and that's why the European Commission has pledged a global quantum flagship program. This just happened this May, where they pledged €1 billion. How many projects have you guys heard where the EU has given €1 billion? You know, we can't build a harbor contract in Brussels, but we can pledge €1 billion for a quantum flagship program where we actually can possess a quantum computer before the other guys do. Oh, and just to kind of give you an idea about what this is actually the chip from D-Wave. These are the D-Wave machines, and this is Leo Kouwenhoven, professor at TU Delft, who's also building a quantum computer and also one of the foremost people in the whole quantum flagship program. And like I mentioned, with a quantum computer, the very real capability to break things like RSA and elliptic curve, this is the challenge that drives the innovation around this area. So are we there yet? Well, the very simple answer is no, we're not there yet. And I suppose the question will be, when will we be there? Will it be 5 years, will it be 10 years, will it be 20 years? And I don't know if we'll ever really know, since the person who's going to get there first isn't in all that much of a hurry to let us know that they got there. And that's only because it would be much nicer if you had a quantum computer that everyone still kept using their own cryptography that they're still using now, which they were very quietly breaking in the background. Furthermore, there is the capture now, decrypt later problem, which is that countries will be making basically copies of all the traffic that they can gather, including the traffic that they would have considered to be gone dark, which is now dark, but will later become clear. So they'll capture everything. I don't know if you heard of the NSA facility in the middle of the United States that's doing just that, the large data center that's capturing all the traffic and is storing it so that when they have this capability, they can actually decrypt it. So what are we going to do about the problem? Well, there are 3 very simple things that we can do. Well, they're not that simple, but it's a 3-step plan. So if we start first about, like, what we can do is we can take a look at the current cryptography that we use and just increase the key length. Let's just start there. The next thing that we can do is actually investigate in key areas of our network where we can actually add quantum key distribution with high demands for long-term secrecy. So if you have data that needs to be secret for the next 30 or 40 years, that's where you're going to investigate putting in quantum key distribution between those links. The third thing that you can do is investigate post-quantum cryptographic algorithms, and this is the future. The real future is that we have algorithms that we can use, and we can deploy them at scale for internet-wide purposes that will be proven to be capable of withstanding an attack from a quantum computer. So if you look at the first piece of advice, just increase key length, actually, it's part of the advice that comes out of Suite B, which is advice that was issued by the NSA to all of its government contractors earlier this year. So what the Information Assurance Directorate of the NSA wants to do is to transition to quantum-resistant algorithms in the not-too-near future. They actually want to go all the way to step 3. But in the meantime, they're trying to say, you know, use a larger key size to protect this classification of information. And when you want to look at quantum key distribution, which is the second piece of advice, how many people have ever used or touched or seen, played with QKD systems? Can I say that even if you haven't actually done it yet, it might be something to consider if you work in the banking sector, if you work in even healthcare, because it's about how long you want to keep your stuff secret. And quantum key distribution allows Alice and Bob to have on a discrete piece of fiber between them a quantum channel, which will prevent Eve from eavesdropping. And this will work because of the fragility and non-cloning principle, where Eve cannot measure or observe these particles without altering them in such a way that Alice and Bob can't figure that out. So what it really looks like, because that was the easy picture. I'll just go back for a minute. So what it really looks like when Alice is trying to talk to Bob, you have a discrete piece of fiber between Alice and Bob. There are polarizers, which are polarizing the light that is on that cable, because this is dark fiber, and you'll have diagonal polarizers. You will already agree what your sequence will be about how you've actually configured your polarizers. So you'll share your polarization configuration to Bob via an offline channel. And then when the photons are sent through the configuration that's set here, they'll be received on the other side that'll be ready and prepared to receive them. If Eve is sitting in between this, she will alter each and every photon that's already been securely transmitted by Alice. Bob will get something else. He'll get gobbledygook. This is a scientific term, I believe. So he'll get that on the other side, and as a result, you'll know that Eve was present, which means that the key that you transmitted over this link will no longer be viable. this presents problems because we don't have fiber optic cables between all of the different places we want to communicate. This is not internet grade. You can't use it at scale. You can't use it for an entire network. There's lots of issues. So one of the things that physicists have thought of is, okay, so in which areas, when we have very high requirements for like massive amounts of security, how can we do it otherwise? Well, one of the projects that occurred is Paolo Villarese from the University of Genoa has actually done an experiment between Las Palmas and Tenerife and the Canary Islands in Europe with a distance of 144 kilometers, where he had basically 2 laser beams between the 2 islands and created a quantum key distribution link over the sea. And what was interesting was, because of all the water evaporation, they realized that even despite those things, they could overcome them relatively easily. What's interesting to note, though, is that they also started doing the first project for doing an Italian-based satellite to have the same type of communication. And what you should know is that it's not just the EU. So if you take a look at China, China is much, much, much further. So in June, or actually in May, they presented their quantum backbone plan, where they're actually having, I mean, this is the great new wall of China. So a 2,000-kilometer network that's relying on quantum key distribution to like present security for the country of China between these points. What they also have done recently is they've also launched a satellite to do quantum key distribution from space back to ground stations on Earth. They're so far ahead of anything that's coordinated at that level in Europe or in the United States, and that's made public. Because what you'll see is in the 5-year plans of China, there's quite a lot of budget going to quantum research, but the resulting research papers are almost nil. So there's a lot of money going there, but there's not that much research, and this is one of the biggest, most public things that we've seen. What's interesting about this is the cooperation between, really the cooperation between universities as well as private corporations. Post-quantum cryptography, really, PQ crypto, that's what we should be doing as a community, because quantum key distribution is going to have its hiccups, but it's available now. Until post-quantum cryptographic algorithms are available, that's a viable alternative. But Tanja Lange and Dan Bernstein at the University of Eindhoven have been working on the PQ Crypto project. They're part of the official EU program, and what they're looking at is different lattice-based type cryptography applications within mobile chat programs, within secure communications so they're really looking at how do we get a PQ crypto algorithm that's also extensible and usable for a lot of people. One of the algorithms that's been around since 1978 is Macalise, but it has some real trade-offs when it comes to processing power and computation. And if you want to do this over a low latency link, it's not that easy to do. What you also see is that the UK government has decided to come up with their own post-quantum computing algorithm, Soliloquy, but Soliloquy suffered some major attacks, and I think that because of the lack of peer review capability that's available to the UK government when developing their own schemes. I mean, this is like one of the first rules of cryptography, that if you really believe in the security of your algorithm, it should be able to withstand Kirchhoff's principle and be able to be open and disclosed and available to be attacked. So Soliloquy was not such a good idea of implementation for how we do this. We should be doing this better. Another thing, which I had you in my presentation before I knew you were here, so is supersingular isogeny Diffie-Hellman. So according to Phil, it's the hottest thing we have. I'm quoting you in a technical way. So post-quantum crypto at internet scale. There's also a New Hope algorithm, which is an algorithm is published together with Microsoft, which is also very viable and also well touted at the moment. So it's really not yet clear what the PQ crypto candidate algorithm will be, but this is the work that's going on everywhere. What should be considered is that without quantum safe encryption, everything that's ever been transmitted or ever will be transmitted will be subject to pillaging by a quantum computer when it exists. So think about that. Old secrets are sometimes just as good as new ones. So it's about preparing now if we want to be secure later. One of the things that KPN did this last May, just before the EU flagship program, is we took a toe dip, literally a toe dip in the right direction, and we tried to examine what it would mean to put a quantum key distribution link between two of our data centers, between Rotterdam and The Hague. It was one link. All we wanted to know is how difficult is it, how easy is it for us to figure out is it actually secure or not, what kind of research and knowledge do we need on our side, and we tried this out to understand what it would mean in the future if we would have to do this at a greater scale. So really, in conclusion, we're just getting started. The whole industry is just getting started. There's not a lot of people that know about this, but I really want to compare this as a really huge technological advantage for anyone who's actually already started with the research, already started with their preparations. And it could mean, really, that there's just going to be the same game as when, just like we had the nuclear bomb and you had the haves and the have-nots, that the person who is going to be possessing viable quantum computers, but also viable post-quantum security, is not going to be willing to share that freely. Because it's going to cost a significant amount of financial, academic, other resources, it's not going to be something that will not be regulated under export control. It'll be a different type of crypto wars. IBM. IBM has the first cloud-based quantum computer. So it's at 5 qubits, and you can all go and log in and get an account. You should just be aware that anything you enter on that platform is the property of IBM. Google is working on a quantum supremacy experiment, and they want to get to 50 qubits within this year. They not only bought the quantum computer of D-Wave, but they also are working on their own ion-based quantum computer. And if you have time, and if you go to YouTube and Google KPN CISO Alert Online, then you'll find a session that we hosted at KPN just a month ago, actually this month, with some of the best people in the field around quantum computing specifically. We're not talking about quantum key distribution or cryptography, but only around computing, and you'll see how far their research has gone. What we'll need in the next coming days, years, months, depending on when it arrives and it's public, is a common way forward. And I think this is probably the biggest thing that we could do together as a community. We also need thought leadership and action in the field of future security controls, because I think we should also be thinking about this just like we think about everything else. How do we attack it? How do we defend it? What are the known algorithms that we have to work with? How do we actually select that candidate? And how can we be part of the community testing it? Also, we need to really think about other options for defense in depth, like we're also used to in the community. What I'm afraid is that we keep building new stuff with old weaknesses built in. Let's not do that again here. Thank you very much.